Today, in honor to have with us Professor Akyildiz from Georgia Tech. He has come here several times and he's friend to several of us. And actually, Professor Strofi was here last week, and Professor Akyildiz and Tony Fermitz and myself, we are in the same project, one of the same projects. And so that's great. So he's of course very well known in this area of wireless sensor networks and wireless communications. He currently holds the Ken Byers Chair Professor in the School of Electrical Engineering in Georgia Tech. And he there directs a laboratory on wireless networking, and he's the chair of that communication group. It's a great laboratory. I have been there many times. And it's great because they do both theory and practice. He's also an honorary professor in the University Polytechnica de Catalunya in Barcelona, and in the University of Pretoria, South Africa. He's an IEEE fellow and an ACM fellow. He has received many awards that will take me at least 15 minutes to go over, which I won't. And his interests are in nano networks, cognitive radio networks, and wireless sensor networks. Today he will talk to us about fundamentals of molecular nano-communication networks.
Okay, so first of all, good morning. Thanks for coming to my presentation. It's Friday. But also I noticed something very interesting that I want to share with you. So I have been here many times. So each time I come back, the room is getting smaller and smaller. I thought I'm getting more and more famous, but then I have less and less audience. What's happening? So anyhow, last time I was here, like I don't know, 4 or 5 years ago, that was a huge room with tons of people. Before I visited ISR, remember, Jaja? And again, it was more, but at least it's not the quantity, it's the quality, right? So it's important. So anyhow, today I will talk to you about, also each time I came back, I had something different topic, like satellites and sensors, and now it's on nano networks. And I got interested in nano networks like 2005. Because my students were on the market for professor positions, and they kept coming back and complaining that many places are looking for nano people. So I got interested in the nano because I went through the microchip era in the 70s when I was in school, and then I saw how the internet and all this high tech took off. And I was interested in when these nano machines, nano devices are developed, how will they communicate? So I got curious, and then I started to work on this, and then I have been to Barcelona since 1973 as a hippie, and then later on as visiting the UPC, and then I suggested them that we should create a center, and we created this in 2008, entry cut. You see a nice logo, like Miro type thing, right? So, so it's a very active area. I mean, center now. We have a lot of research projects going on, and I'm with Georgia Tech since 1986, like 26 years now. So, the guy who hired me there just came here, Ray Miller. So it was nice to see him. Okay, so. The story started with these two people from España, like Brunetti was from Madrid, and he had already a PhD in sensors, microsensors, and then Cristina came from Barcelona. And when I had this idea, I told them that we should really look into these nano devices, how they should communicate, and they didn't like it. That's always like that. The first time, they don't like something brand new, like getting into this unknown ocean territory. So I pushed them, and we worked very hard, like a couple of years, and then we put this roadmap paper together. And that time we thought the only way to go that these nanoscale machines communicate is through molecular communication, learning from biology. And the paper was more focused on molecular technologies. And even we said that forget the classical way of doing things. And then in 2009, Josep Jornet, also from Barcelona, joined my lab, and he said he will really revisit the EM case, the classical way, and look at these nanoscale machine communications from the EM perspective. And then we realized that we can do that but we will operate them in the terahertz band. And as some of you may know, the terahertz band is active now in 8.15.4 interest group. So we wrote this roadmap paper. And then the last November, I was invited by Communications of the ACM magazine / journal. They wanted to have something on this topic, and then we put both of them together, the molecular track and also EM track. And even they liked this topic that they put the cover page as this nanoscale machine communication. So it's a very nice design. So what is nano network is these are nano-enabled, nanotechnology-enabled devices. The most basic nanoscale functional unit, like a computer, like processors, data storage, like memories, sensing devices, sensing units, and also actuating units that are all in nanoscale, also antennas. Okay? And then when these nanomachines are built, they need to somehow communicate, right? And that's what we are talking about, nanoscale networking. So how we can connect these nanomachines so we can execute complex tasks and then communicate through these nanomachines. So now these nano people, nano device people, they are taking 3 different tracks so far for the development, design of these nanomachines. One is so-called top-down approach, taking these microscale level machines and scale them down to the nano level. Okay? That's called top-down. And the other one is bottom-up approach, and then you see there are 2 tracks. Okay? The bottom-up approach is starting from scratch and creating these nanomachines. Okay? For that, they have these nanomaterials. I'll explain them to you. For example, graphenes. Okay? Use those graphenes and develop these nanoscale components, modules, and then accordingly nanomachines. So that's this track. And then the other track is, the top one, go to the nature, because in nature, I will also demonstrate that to you, there are a lot of nanoscale machines. For example, human cell is a perfect example for a nanomachine. So now, can we learn from nature and then re-mimic these natural phenomena and create these nanomachines? And it's kind of like the biological track or the natural track, like learning from them. I will also demonstrate to you and then convince you that indeed these components in the nature that we can realize in our physical world. And then the third approach is, again, hybrid, meaning some components will be nanomaterial based, some components will be learned from nature, and then developing these nano devices. So I'm talking still about device level. So this is still going on, and there is no winner. Which topic, top-down or bottom-up approach is better? There's nothing so far the winner. The same thing, which one is better, nanomaterial-based or organic-based? So people are still developing these nanomachines. And if somebody comes to you and says, I already hear that here and there sometimes, oh, we have nanomachines, they're lying. There's no nanomachine existing already. I'm talking about nanomachine, everything, modules. And so, yes, nanoprocessors are existing. I will tell you about that. But a complete nanomachine is not existing. So please keep that in mind. So, when you look at this bottom track, this is called nanomaterials. So the most famous one are, like in the past, were nanotubes and nanoribbons. Now the graphenes are up and coming and running. And in fact, in PMRC, Chandler was there, conference, it was October 2010, and I mentioned this really as if I had talked to the Nobel Prize people, that the inventors of the graphenes will receive Nobel Prize someday. And I was expecting 17, 20 time frame. And exactly 1 month later, they announced, these Andrei Gaim and Konstantin Novoselov, they are both Russians, but they work at the University of Manchester, that they received the Nobel Prize for 2010 in physics. They are the inventors of the graphenes. The graphene is a 1/8 thick planar sheet of bonded carbon atoms in honeycomb crystal lattice like this. And then the carbon nanotubes are like these folded nanoribbons. They were invented in 1991, and then graphene nanoribbons were invented in 2004, which is a thin strip of graphene. Here is an example that graphenes are really taking off. Is there are these flagship activities in the European community. I'm involved through the N3 cut, and graphene, that's the title of that. It's like 13, 14 years effort, like several $billion. Some of you say EU doesn't have any money anymore, but they do. So they are trying to create these flagship activities, and one of them is graphene. The other one is called guardian angels, like nanosensors, and there are some more, like there are 6 finalists, and next year they will decide who will be the winner. So graphene is really, please keep an eye on that. It will catch up more and more. So now, can we use these graphenes to create all these new components, like batteries, memories, processors, antennas, transceivers, in the nanoscale? Why? Because these graphenes have been analyzed in terms of electrical and optical properties in light of quantum mechanics. They have high current capacity and high thermal conductivity. That means they are very energy efficient. That's what we're also looking for, right? Energy efficient resources. Extremely highly mechanically strong. They are robust. And also they have very high sensitivity. And that's why they have very high sensing capabilities. So having all these nice properties, we may use these graphenes and then develop these systems. So now I want to show you an abstract picture of a nanomachine that we are visualizing, and then talk to you about how these nano components are being developed, what the state of the art is, and then of course we'll go to the biological track, which is more topic of this presentation. So now this is the typical nanomachine that we are still using, like batteries here, nano sensing unit, actuator, memories, antennas. So like the way that we know. So one of the challenges is not only developing these modules, but also putting them into this platform, you know, kind of like integrating these modules. One of the research solutions is they call this DNA scaffolding. So now take these components that you have seen and integrate them using these DNAs, like adenine. It's kind of like the female of the thymine, or guanine is cytosine. So now what you do is you take this strip of these DNAs and then glue them in these components, for example, and then you glue them through these DNA male and female portions. And by this way, they will try to create these devices, integrated devices. So this is still going on, how, when these modules are developed, how they will be integrated on a platform, for example. Now, these devices are also components. I'm talking about components now. The physical nanosensing units, for example, they have these carbon nanotube here as an example. If they have external forces, they can sense them. Or chemical nanosensing units, like the gas molecules, they can sense. They're existing separately. Or biosensors, for example, they're also existing. Sensing units, not sensors. I mean sensing units. Then my colleague ZL Wang, who is very famous in this area, Nano Batteries. You see these zinc oxide wires, like, you know, it's like very, very, you know, infinitesimal small wires. They can generate power from these vibrations, and he has them already. So he demonstrates them, but again, as a separate, standalone components. The nanoprocessors are already in our latest laptops. You know, when you have the newest laptops, they have these 32 nanometer processors in them. And then the 20 nanometers are coming out. And in the University of Manchester, they had the world's smallest processor, like 1 nanometer. In 2008, you see under the microscope on the right-hand side. So the nanoprocessors are already on the market here. Okay. And now the nano memories are also being developed. Okay, again, using these nano materials, right? And the objective is try to create single atom memories. In other words, store a single bit in a single atom. So if you never heard of Richard Feynman, it's disappointing because he's a very interesting character. And you know, he was one of the very important people in the Manhattan Project, for example. Some of you may remember Los Alamos National Lab. And he actually used this word. There's plenty of room at the bottom in 1959 when he gave a talk. And that's a very famous talk. And then he got in 1965 the Nobel Prize. So he gave an example. 5 by 5 by 5 atoms were used to store a single bit to avoid inter-atom interference. That makes 125 atoms per bit. And there are computer science people that are using this DNA. Maybe you heard of DNA computing. They are using 32 atoms per bit. But the objective is a single bit for single atom. And that's going you know, well now. People are developing using so-called gold nano memories or magnetic memories. And they will have gigantic capacity for the storage. You can imagine for very small devices, you will have a very huge capacity for storage. And also, when you go to the antenna conferences, you will see several papers on nano antennas. People are trying to develop these, like a single carbon nanotube or a set of them, a nano-dipole or nano-dipole array. Then we have developed all designs. These are all designs, by the way. It's called nanopatch antennas or atom precise antennas. This is also very active. People are trying to develop these nano antennas.
What's the range of those?
The distances, I will come.
The range?
I'm coming, I will come.
Second
It's
question.
very, very, yeah.
Why electromagnetic zone?
What is that?
Why electromagnetic zone?
I'm coming to that. Wait, I will talk about the limitation. You jumped to me into it. So I'm just explaining you where the devices are, like the components are. So when these components are developed, then they need to be also put together, right? These are all question marks.
Can I add something to what you just said?
Yes.
Actually, people forget, you and I don't, because we are older, that the main reason why controls and communication were created is to create devices from components. Back
Yes.
in the day.
Yes, yeah.
So it's coming back.
Right.
Because of this device.
Right. So, now let's go through the natural track. Okay? So now, I want to demonstrate you there are a lot of nanomachines in the nature. Like these eukaryotic cells, or cells like neurons. You can see, I will also demonstrate you all these components like mitochondria, nucleus, and all the other ones that you will see, gap junctions. They are really a nanomachine in the nature, or bacteria on the right-hand side. Bacteria has these messed up internal organs, but still, this is much more orderly than the bacteria. But anyhow, that's also a nanomachine in the nature. So now you can see also these nanomachines in the nature, they communicate. On the top, you can see the eukaryotic cells, like 2 nanomachines, and they're using molecules like proteins, ions, and hormones, and pheromones, we'll see those. They communicate with each other through these molecules. And down there, you can see the bacteria are also communicating, as you can see, either as nanomachines, bacteria, and then they have these so-called chemotaxis process. They bind to each other, right? Or they can also do like, bacteria and then release molecules like DNAs or autoinducers, and then they will be captured by the other bacteria. So this is already existing in the nature. So now let's take this cell, the eukaryotic cell that I told you, and look at all these components again, step by step. So you can see there's this nucleus DNA, there are vesicles, gap junctions, receptors, and mitochondria. So now, can we learn from these components, develop these components in our physical world, and then also create this nanomachine, which is inspired from the nature, right? So now, here is a very good example for energy sources. So what happens in the cells is, cell gains useful energy. It combines glucose, amino acids, fatty acids, and oxygen. Okay. And then there is this so-called ATP, adenosine triphosphate. That is the energy created for the cells. You know, sometimes you say, oh, my sugar level is low, my energy low, because the glucose level is low, for example. Now, you can see this under a microscope. It's a mitochondria. I couldn't even pronounce these things correctly. My biology friends told me it's called mitochondria because I was saying different words. So mitochondria. So it's under a microscope. So it's like, you know, getting all these amino acid, fatty acids, and glucose and all that, oxygen, and then it creates energy, okay, for the cells. And indeed, this concept is already being used in the, it was even in CNN news last 2 years ago, that there are some concepts already that they are creating the sprays that they will spray on your cell phones or mobile devices, and the mobile devices will gain energy. And it's exactly based on this idea. Of course, don't go and try to find them. They're not there in the market, right? So that's, you know, it's going on. It's not science fiction. Right? So now here is Biotransistors. These pictures are from IEEE Spectrum last year. So they had a special issue about this. Like as you can see here, how can we design a cell in the same way we design a silicon chip? Okay? How we can create biological transistors based on protein synthesis from DNA, as you see on the right-hand side. So DNA and synthesis. And then what we can do is we can create these devices which are producing silicon chips, but the silicon chips are hitting these Moore's law ceiling. I'm not an architecture person, but now we can try to create these new chips as cells, living circuits. And we can expand this capacity of these chips, right? And then, of course, accordingly, they will have much more powerful functionalities than just the silicon chips. That's why we are saying that their capacity will go up. Then, can we also create transceivers? Like you can see, this cell releases these molecules, like proteins, as you can see here, and they're floating around. Can we mimic this and then create a transceiver? And then, you know, it will release molecules, kind of like messages, packets, right? And the same thing, the cells are receiving, like, you know, these molecules in the nature, and this process is called ligand binding process. Like these molecules are coming, and they will be sucked by the receiver in this case, and that's called ligand binding process. Sometimes they get lost. Okay? So now, can we mimic this as a receiver, and then create our receivers for our machines? So these are question marks. Next question mark is, here is an antenna from a moth. Like, you know, the animals are communicating. They all have antennas, like in the picture that you see here. And the pheromones are, for example, coming, and they will be received by all these like cuticles and all that, and they will be evaluated. It's kind of like receiving signals, and then they will be evaluated by the receiver. So now, can we learn from the nature and then recreate these antennas and you know, realize these nanomachines?
Why you work this antenna?
Which one?
The pheromone?
No, like this antenna is from the moth. I mean, all the other antennas are also like
But
animals.
It's not an antenna in the way we mean it. It's a chemical communication. Okay.
Exactly.
It's not an antenna.
Yeah, but that's what we are trying to learn, and then also realize that can we do the chemical communication in our world? I'm coming to those two, right? But you know, I'm trying to find the bridge. You know, they don't call antenna, but at least that's what, you know, in our world it's kind of antenna role, right? You're receiving them and evaluating them. Okay. So, and then long term, the next 20 years, I think we will have machines that they will have certain parts from the nanomaterials, from the first part that I explained to you, and second part maybe could be like learning from nature, and they will be put together as a hybrid nanomachine. Like you can see here, like zinc oxide wires, and then biological nanosensing units, and then maybe we can also have the batteries learn from these mitochondria roles. So that will be, in my opinion, the long-term solution, coming up with hybrid components and hybrid nanomachines. Okay. Now what I did so far is I explained you the components, what people are trying to do. In my opinion, the first track will be faster, like doing all these nanomaterials. The second track will take longer, because it's not easy really to map everything to our physical world, like the nature. So now, once these devices are developed, and they can be used for many, many applications, especially when they are put together and they create these networks. One of the applications is, it's kind of like intra-body nano networks. I mean, now there are these body area networks. I'm not talking about those. We're talking about like intra-body nano networks, like these nano devices will be injected into the body, for example, into the blood, for example, and they will have zillions of them, like white and red blood cells, and they will be like additional cells, and then they will communicate cooperatively. So there's a nice cooperative communication, and then they will attack the viruses and bacteria, right? So it sounds very science fiction, but that's the reality. And so now, and all these diseases that we can imagine, they will be history, like all this diabetes, and like Alzheimer's, epilepsy, depressions, and then cancers, hopefully, and then malaria. So the list goes on and on. So that's in the medical field, there will be huge revolution. My opinion is, again, once we solve all of these the next 30 years, and I'm sure the nation will give us other problems in terms of health. So I say that the human life should be prolonged to 200 years, but I think there will be other problems, so that we will somehow be fighting.
This famous medical person in England says there's no reason why we cannot use telephone.
That's right, but I'm a little bit more conservative. I said 200 years. So, but now here is another example that we can learn from this nanoscale communications, like the neurons, the cells, with both electrical and molecular links to other cells. And then we can study those communications of these nanomachines, and then what it will help us for the medical people is, they can understand better how in vivo networks of neurons work. And then they can try to create these diagnosis and treatment tools, for example, for brain pathologies. Okay? And then here is another application, like the heart muscle cells, okay, the cardiomyocytes. And they are interconnected for heartbeat synchronization. And they also use molecular and electrical communication. And again, when we learn, understand how these components are communicating, then we can also develop according diagnostic tools and disease treatments. And now here is another world that is called bacteria communication, bacteria. And I did not know this actually. Bacteria are also helping us, by the way. You know, the humans, we all, you know, I'm working with biologists and medical people. So indeed, we all have bacteria in us. But sometimes you go to a country, then you have some problems because you say, I'm not used to your bacteria. So that's a typical case. And we have to have these bacteria. And then the bacteria are, there is this notion called quorum sensing. That's the gigantic cooperative communication. Like collectively, They work, millions of zillions of them. They work together. And what they do, for pollution control, they can be used. Then they can clean residual waters, by the way. And they can also clean pipes. So they have a lot of useful roles that they do. But what we learn from them is, again, bacteria is a nanomachine, and how they create colonies of bacteria, how they communicate, how they do quorum sensing. That's what we will learn as communications people, and that's what we want to somehow apply in our work, right? So now this cooperative network behavior, as I told you, quorum sensing. It's also interesting. There are these man-made machines. One of them is also, like there are these biologists, they take bacteria and engineer them, they program them. Like, synthetic bacteria, for example. And they are programmable. They can be genetically engineered, and they also carry DNA information, and you can somehow guide them, monitor them. Because I will also talk about the project that we have. So we are working with those guys. It's a very interesting world of bacteria. So now another thing here is Internet of Things, or nano things, right? So now everybody talks about cyberspace and Internet of Things. Now we are also talking about nano things. You will have inside of our body, outside, there's zillions of these components, machine to machine. They can also be on the nanoscale and having all these nano components. And here, future Internet after that, this is like 50 years down the road, all the machines, I'm 100% sure that all machines will have nano components in them, fully nano components. Nano components doesn't mean that humans are made of nanocells, nanomachines, right? Well, we're not that small. So in other words, what I mean by that is we can have base stations, normal base, but all components are nano. Or we can have the gateways and switches, or mobile devices. They can be all nano components. But what is the gain of it is, remember AI, that was hot topic in the cognitive science in the 80s. How can we create human-like machines, intelligent and all these capacities? And with the nanoscale devices, components, we will reach that. That's why I strongly believe, all these future devices will have nano components in them. And accordingly, the internet and all this mobile, everything will be nanoscale. And then advanced health systems, we talked about it. Just showing another, like mobile health stuff, right? That could be also part of this. And then another thing here is these chemical attacks. When you use microsensors, when you put like this type of environment, and when there is an attack, biological or chemical attack, once they detect it, it's too late already. So you are dead. So because they are not that highly sensitive, highly fine granularity sensing. Where with nanosensors, nanosensing units, you can capture those chemical attacks and alarm them. So these are some examples. Here is this terabit wireless networks. Right? Like how can we operate these terabit per second wireless networks? And that's kind of like 5G, but I think it will be like 6 or 7G. Or here are terabit, kind of like gigabit Ethernet optical link, and then terabit per second links between these devices. And here is another one, like terabit access networks, like this, kind of terahertz wireless access networks. And then here is another one, multimedia kiosks, and wireless, very close, short range. You can download zillions of terabytes of data very fast, for example. So these are some examples, but the most driving example is coming from the medical field, as you have seen. That's more exciting. And the other ones, we can always twist existing technologies, but the medical cases are very promising in my opinion. So now let's go back to what we did. As communications people, we try to investigate both tracks, like EM-based and the molecular track. So the EM-based, with Josep, we did this work. We tried to see how these nanoscale machines communicate. And we investigated that, and we ended up in the terahertz. Now, I will also come to your question. So now, we developed this mathematical model and calculated the total path and then the noises. And then we have seen the terahertz band is very unique. It's like 0.1 to 10 terahertz. Okay? Because there are so many channel models, propagation models for the gigahertz and megahertz. They're in the textbooks. Why another channel model, right? So that's why we wanted to emphasize there are some uniquenesses there, right? So now what we did is, I will show you the formula. This is a classical total path formula, total path loss formula, like spreading loss and absorption loss. Spreading loss is the same, but the absorption loss is really showing these peculiarities of the terahertz band. Because, like here you can see this spreading loss, but the absorption loss, you see all these gases and water vapors in the channel. They do not play a role when you're in the gigahertz level. But when you go to terahertz level, those gases and water particles, they really screw up the signal propagation. And they're all captured in this absorption loss. You can see here, like reference temperature, system temperature, molecular volumetric density of each gas, and etc. They're all captured in this formula here. And then accordingly, we can see that the terahertz band, and then accordingly the noises also are affected by these gases and water particles. So what did we learn out of this uniqueness of the terahertz band and what we learned from it? We have, there's a lot of math, but I skipped those. What did we learn is the terahertz is affected by the presence of different molecules in the medium. And then high molecular absorption attenuates the traveling wave and introduces noise into the channel. Okay. So now here is the picture that we learned, like depicted. Now you can see there is a terahertz band, like from 1 to like 10 terahertz, and these are the distance. Now your question, right? So two devices, like 1 millimeter, 1 meter to 1 kilometer. So now you see they are extremely distance limited. So now you can see the red area is like it's impossible. The loss is so high that you don't have meaningful communication, right? But below 1 meter, you have these areas, it's kind of like windows, right? And then you can try to still communicate and have meaningful communication. So they are distance limited. So,
Can I ask a question?
yes.
Okay, since you are going through different chemical molecules.
I'm not here chemical, I'm talking about EM.
No, the medium is chemical. It's a physical medium, so it has molecules, right?
Yeah, but in gases and yes, yeah, okay.
Right. So,
But the communication is EM.
it's not.
Yeah.
But in other parts of the physics work, people have tried to modify the chemistry to amplify the signal. Okay. So in other words, as I said, the signal, this causes a chemical reaction which actually carries the signal across. Has this occurred here at all? This thought at all?
No, we look at the second part when we talk about molecular communication.
You're using the medium that
Yes,
communicates through. One is
we did that in the molecular case. We are just looking at from the chemical perspective, and then we look at all of these in our models. But here we are just saying we want to do classical way of EMs
classical EM.
and a terahertz band.
So this is just an obstacle.
Right,
It's
right.
not used to calculate.
No, I'm just trying to show that can we go with EMs and nanomachines and communication? Yes, we can, but we are distance limited. That's what I'm trying to show.
Because for instance, in underwater communication, right? In underwater
Okay, so what you tell me is it's more my future objective hybrid cases.
Correct. Because in
Right.
underwater communication, we use that. We use the fact that if I change the salinity
Okay.
and other properties, I can create long wavelengths.
That's true. And that's another thing that we wiped out the acoustic communication, for example, for these cases. Can we also use that? I don't know, but maybe revisit. But what you're saying is more like hybrid case, that we can do, once I want to understand this, and then the other part I will demonstrate to you 3 hours. No, but then, you know, we'll see. So we are trying to, I'm trying to show you the classical way. In fact, we are also in this interest group of terahertz band, so we present all of that, so it's going well so far. So now what I'm showing you is, this is the case that we learn. What did you learn is, we are very distance limited, and then also the water is, the enemy of the water particles is the enemy in the terahertz band, the biggest enemy. So, but the gain is we have gigantic bandwidth. Like you can have terabit per second easily. So if you try to find a way, as John said, maybe, you know, amplifying and all that, to increase the distance, that would be perfect, right? But it's distance limited, like below 1 meter between these components. Okay. So you know, what we did is, this is a commercial now for our work the last 3-4 years. So we did some work on the nano patch antenna as a design. I will come back to that we are trying to also you know, finish the design and do some experiments the next 3 years. Then this work that channel modeling capacity analysis was published in ICC and Transaction Wireless Communications. And then we did some modulation schemes and network capacity analysis for SECON conference. Then we looked at the low-weight channel coding scheme. But you know, the interesting thing here is that we are trying to use avoidance, like, you know, remember the CSMA collision avoidance? Now we are saying, can we also avoid errors before they happen and they try to are detected and corrected? So that's called like low-weight channel coding. We learned it from many, many years ago from the computer architecture. We try to use it here. And then we also developed, by the way, here in the modulation schemes, we developed this time shift on and off keying, T-SOC, with very femtosecond long pulses. It's like learn from ultra-wideband, but these are femtosecond long pulses on and off. But there was another novelty there is, we do not transmit zeros, we just keep silent. And having silence is perfect because, you know, we are not using the channel. So we are trying to find an encoding technique that it will take the messages, it will create more zeros than ones. Because, you know, keeping silent is better, because then we will avoid all the errors in channel effects. So these are all explained in those, in that paper. And then we have energy harvesting paper, and then my other people in Barcelona, they developed a MAC protocol. Again, all the physical layer effects there. And then we have also nano transceiver design with the Barcelona people that will appear in ICC. So as you see, these are all design and, you know, ideas, concepts. And the objective here is this project Granite. I hope that the government will support us soon. Graphene-based networking, Granite. And we are working with MIT guy, Thomas Palacios is a device guy there, an antenna guy, and also Kyung Oh is in UT Dallas. These are very successful people. We have this team. We are trying to, what we want to do is really very simple device here. That's transceiver, antenna, and then another one. And then we just want to look at one-to-one communication the next 3 years. So it's a long way to go, okay? So we want to do prototype, right? So just simple model, and then do all our mathematical modeling, analysis, experimenting with one-to-one, for example. Okay? And by the way, same concept is like under the name grant is by the European community at UPC. So granted and grant. Okay? So now let's come back to the, some of you say we came here for molecular, you talk about EM. Well, I want to share all of these things with you. So now there is a strong statement, and in fact, I don't take the credit for it. 2000, one of our biology professors, he was acting vice president at that time. He was giving a speech at a dinner table, and I said, "What a BS," you know, because he said the 21st century will be the century of the molecular world, biology world. And all the new inventions will be done in this field. So I was thinking, what the heck is he talking 12 years ago? And indeed, over the years now, after I got into this area, and I strongly believe that the information technology era is coming to an end, like all the empires, right? Look at the Ottoman Empire, Chinese Empire, Greek Empire, Roman Empire, US Empire. So they're all coming, no, really, this is the history, you know? So the information technology era is coming to an end in like 80 years. It started in the 50s, right? And it will really fade out slowly. And all the new era is the molecular technology era. It already started, but the real wildfire will catch in 2020, in my opinion. So we are still a long way to go, but
We'll never have.
ideas are there.
We'll never. Without information, knowledge, the seven cannot happen. I can put this in writing.
Okay, so we can learn from that. I didn't say it will be wiped out, but in 50 to 100 years, that will be obsolete. Everything will be based here.
Nope.
Okay, we can put a signature and then put it in history.
It will be called molecular IT, but it will not be.
Okay, but the word is there. I mean, you can also call it, Greek, Roman, what is the empire, but is it still, okay. I mean, I don't care how you call it, but it will not be the way that we are used to this IT.
That's different.
Okay, right, that's what I mean.
So you should say conventional IT technology, or the current technology that used.
That's what I mean.
Clarify.
That's what I mean. Okay, so the molecular communication is a new interdisciplinary field. Okay, now here's another history, and again, we're all timers here, that since 30, 40 years, always they say work together, like NSF, Department of Defense, build teams, and we are in the Mura, for example, right? So, but it never occurs the way that these agencies expect it, because most of the time I say I can do it myself, I don't need the other people. That's really the truth, but here it's indeed an interdisciplinary research. So some of you may be saying, my God, I don't want to learn biology. Indeed, then you have the biology friends and colleagues that you can work with them, or the physics, chemistry, medicine. So it's a truly interdisciplinary research that you need each other and you learn from each other. And I went through those phases the last 5 years, talking to those people. It's very difficult because they have different language and you have to teach each other, but it helps you a lot. Apropos, I hated biology in the high school, but I didn't need to learn biology because I have my colleagues. You know, I asked them about how can you use this, that in your field. They explained to me and we explained them the communication aspects. That's why you need them. But if I want to develop an algorithm, why should I get to computer science class or operation research? I can develop it in my lab, for example, because I know the theory and all that. But there, I don't need to learn all the things again. You know? So that's why it's really true interdisciplinary research. So now, this is a picture that we keep fixing. The first one was very primitive, but this is like the based on the ranges, like short range, medium range, long range. Okay, medium range is blah, look, nanometer to micrometer distances between these devices. Some of you will say, where can I use it? There is this notion of, I'm not an architecture, but in Barcelona we have a supercomputing center. There is a big guy there, Mateo Valero. So he said, can we create this network on chip multi-cores? Like, they are all close to each other, right? So short is a medium range, and then long range. And then we did this wireless, but in fact they're all wireless. But because they are so close to each other, that's why we call this wired. In fact, in reality, that's wireless. So there are these in the nature again, molecular communication. Molecular motors, ion signaling, like the most important one is the calcium signaling. Then the medium range bacteria like chemotaxis, and then long range pheromones and pollen and spores. And can you learn how these natural communication systems exist and then remimic them in our field? Right?
So where do you put hormonal communication?
Hormonal communication will be all in between, proteins, right?
But that's primarily long range, right?
No, proteins are hormonal. It depends again here and then actually here.
Because they use the blood to communicate. But
It's here.
Long
Here.
They're long?
But they are not, they are still also short, right? They
There
go.
are some, but they are close.
So yeah, they're all here. Okay. Now I have also some cases, the example that you call it like capillaries, for example. They're on this here. Okay? Like because it's a long range.
You see?
I remove those because it's too much.
What I don't like of this chart, if I may say something,
Sure, go ahead.
is this attempt to try to say wire the wire.
That's why it's mentioned that we should remove those. But I each time I fix these things. So like I had capillaries. Now you mentioned that I should put it back there, right? Capillaries is really indeed it's a long range, and then there's also this these nerves that
nerves are
right. So it's also long, right? Long range, 1 meters. I had those in one of those slides. So now let's look at these cases very quickly. What is a molecular motor? As you see here, a devil-looking type thing. This is indeed from the microscope. So it has like it moves like 1 step and then 2 steps back. So and then there are these microtubules like rails. That's why we call it like wires. But in fact, they are still wires. The devices. When you look at the big picture like this, like 1 nanomachine here, another one, of course, very short distance, right? These devil-looking proteins or molecular motors, it has this vesicle. It moves very, very slowly. 500 nanometers per second. Talk about delay-tolerant networking. Yeah, it's like funny for computer science people. Like here's a delay-tolerant network, and bacteria need 4.5 hours to move 1 centimeter. So it's a real delay-tolerant network. So now you can see, they are moving like that. So what we do is we will create message. That's another challenge. How will we create the message and put it into vesicle, cargo of this protein, of this nano transporter, right? And then it moves like with these feet on this microtubule, which has 25 nanometers, and then go to the destination. So all of these.
The analogy you described it, okay? Some people say this is more close to a nano dimension post. I have the carriers and the envelopes.
Yes.
The carrier envelope.
Exactly. Right.
It's another metaphor.
Yes. Here is one of the ideas here is, can we use DNA encapsulation and create these messages like you can see there and put them in the vesicles and then transport? But it's in ongoing research. So if I may, in fact, Tony Efremidis, he listened to me once in one of his keynotes. He said, "Oh, you took the same classical way of all the steps." I said, "Look, we are still learning." So I try to find bridge to our world. It doesn't mean it must be exactly these here. Maybe not. Well, what we are learning, somehow I need to tell to communication people, like these classical steps, right? Encoding. How will we select the right molecules that represent information? Then how will we attach the information packet to the motor in the cargoes, right? And then how will they propagate? Very slow, right? And then how will they be received? In other words, they will be detached, downloaded or detached from those vesicles. And how will they be decoded, right? At the end. So these are all question marks that we need to answer. So you can see that's like one step could be 1 PhD, for example. It's not that easy, right? Same thing with calcium signaling. That's the second portion. Now, how can we encode the information in calcium ions? Now we are in this chemical domain, right? And then how will we initiate the signaling of these ions? And how will we propagate these calcium waves, calcium ion waves? And then how will we receive them, the concentration, and then decode them, right?
I mean,
and all decode meaning in this case reacting, they call it reaction.
The answer to Tom's question is pollen, right? The light blue ribbon you have is the symbolic representation of the processes, and the yellows are the physical representations.
Exactly.
And this can differ.
Exactly. Yeah, but I mean,
For the audience here, because we work a lot on cyber physical systems.
Good, so you understand, good.
This can be examples.
I just mentioned that somebody may say, why we are still doing this classical way. That's it. That's why I'm trying to map these physically exactly, and how we may not have all the steps that we do in classical way. I don't know. I really don't know the answers. Now, the problems of this molecular case is that the velocity is 500 nanometers per second. As I told you, it's very, very slow network, so communication. And then also another thing here is molecular motors, when they are longer distance, they detach from these rails, microtubules, you lose them. The other one is unidirectional communication, and then of course, very, very long communication delay. Same problems with the client CNC delay. So now the bacterial communication, we have this paper that we published in JSEC in May 2010, that is with bacteria. This is E. coli bacteria. So now you see, this could be also mimicked as a nanomachine, like these nucleodes and then the plasmids, the flagellas, and moving around. You can put your messages here, and then you can carry these messages. And it's very interesting. I observed that when bacteria merge, chemotaxis process, they eliminate. There's, you can observe that in the microscope, because there are like millions of these in the colonies. And they're all working in the colonies that, talk about mimos, million by million mimos, right? No, really, it's very, very interesting world. So here is again, the actual steps, and then how we can convert them. So one of the challenges is, how can we create these DNA packets, messages, and then put them into these bacteria cytoplasm? Ideas are like plasmids, bacteriophages, or bacteria artificial chromosomes. And then the transmission, propagation, reception, I put all in the Wonders umbrella, because they look at sense gradients of attracting particles in the real life. And they move towards direction and find more attractants, the process called chemotaxis, where they merge, right? And then they merge, meaning bind to each other. And the receiver releases attractants so the bacteria can reach it. That's also the distance issue. And then the extracting of this DNA packet from the plasmid using, for example, restriction and the nucleus enzyme process. So now, how can we learn all of this and remimic that the bacteria case in our world? Plus, of course, all these things about cooperative, like quorum sensing, cooperatively they will work and communicate is a problem, because here we are only looking from single transmitter and single receiver perspective, but there are in reality millions of them. Right? So how will we capture those? And here is another example with the long-range communication using pheromones. First I thought like elephants can smell like 20 kilometers, so we said that several kilometers, but then we realized we should be more conservative. It went down to 1 kilometer. Like pheromones, each animal has its different pheromone. Like tigers have different pheromones, and donkeys and elephants and all that stuff. Thanks God to the nature. You know why? Otherwise we'll have a lot of mutant creatures in the world, right? No, seriously. Yeah, so really.
No, because the genetics is not good.
I don't know, but sometimes it happens, in some of the, yeah, but, so only, so now that's why I said that. How do we select specific pheromones, like kind of the message type, and then transmit the information and produce the reaction and the intended receiver? And then they release the pheromones through liquids or gases, and then they are diffused into the system. And now the reception is called ligand binding receptor process. That's a very complicated process that, again, a lot of losses happens. You don't, bind it to this coming in pheromone, for example, and then decode it, because different pheromones trigger different reactions. So now, when you look at this pheromones from the nature, that means we'll have zillions of mimos in and out. Like you can see, like different colors, receptors, blue, etc. That means each of them can receive certain pheromones, right? So where will they end? How many receptors will they have? So that we can create these receivers which can interpret different pheromones.
And they're actually interacting with each other.
Yes, 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 exactly. So now, having told you all these natural phenomena in the communication aspects, So now let's go to our domain, the communication domain. What are the needs? So now I always say, who wants to become the new Shannon, right? So can you create a new information theory? Okay. Then I will explain to you some of the challenges there. Now here, all the design and development nanomachines are the domain of the device people, right? We need modeling tools, not only for simulation of the communication, but also for the device people, modeling tools and simulation tools. Normally we all are using like discrete event systems like this queuing theory, queuing models. Here they are trying to use automata theory models. Like automata theory, 1976, I took the classes on automata theory and cellular automata. And I was thinking, I love that, by the way. And then when the cellular automata, it was saying that the machine produces itself, and I was saying, what the crap is it? You know? Self-reproducing automata, cellular automata. And now, many years, 40 years later, people are using those. Mealy automata, Moore automata, cellular automata to model the nanomachines and understand the components, and then also for communication perspectives, right? So it's coming back again. And I went back to the Google, and I found that so many results came out in the cellular automata. There was this firing squad synchronization problem. So we can really learn a lot of these from that area. So then other thing is about communication, architectures like topologies, and also the protocols, communication protocols. Not only just the MAC and routing and all that stuff, but also, in fact, all those steps that I showed you, right? Encoding in our language, propagation, reception, decoding, all of the above. Right? Error control, they're all open questions.
Because it doesn't happen in the examples you gave one-on-one, it's many all the time.
Oh, that would be, yeah, right. But my suggestion to the young people is start with one-to-one, Otherwise, that's what we did actually.
That brings the nerve down to everything.
Yeah. So what we did is we took this. The time is getting short, right? Right. So I will. This one appeared in JSEC in 2010, but we did a vanilla analysis. Vanilla analysis meaning we don't have anything noises, anything, no problems, right? So simple transmission, diffusion, molecule, and then the reception. You can see here, like, two nanomachines and all these molecules are floating around, and this is kind of like diffusion process, okay? And then we try to analyze in terms of path loss and delay, for example. But there are many challenges here, like this source behavior, destination behavior, and these particles or the molecules are floating around, right? So what the questions were to answer in the transmitter case: how chemical reactions allow the modulation of molecular concentrations as transmission signals. Then propagation: how the particle diffusion controls the propagation of modulated concentration. And the receiver is how chemical reactions allow to sense the modulated molecular concentrations from the environment and translate them into meaningful signals. So these were the question marks that we answered, and the model. And then we looked at attenuation of the end-to-end model, and transmitter, propagation, and the receiver, and also the overall delay formula. And these are the model that we developed, the formulas. And for the channel model, we went to 1875 by Adolf Fix, right. So the Fix law 1 and 2, and we use that for our channel model, capturing this diffusion in the channel. Okay. So now next question was, after that, this was a vanilla. There were no problems, noise, and all that stuff.
The population of molecules in the channel was a single population, uniform.
Uniform, yes. Homogeneous, right. That's right. You got it. That's why I use the word particle. The molecules will be multiple. You jump into the more different case. But anyhow, but it makes sense, you know, slow, like here. In the next one was noises. So now, I believe that the noises are different than the classical noises. Okay. So now we said for the transmitter side, we call this particle sampling noise. Particle sampling is, these are continuous systems, right? The molecules are released. Now we need to somehow find discrete points to sample them. And sometimes we may miss on this sampling because of this decision, right? And then propagation side on the channel, it's called particle counting noise. So now we would do snapshots in the channel and say, oh, this many particles are there. Maybe that assumption is not correct, and you know, we may lose some of the information. And then the last one is, it's called chemical noises. On the receiver side, it's called ligand receptor kinetic noise. And that also we analyzed it. So the first two parts, the noises, we published in transaction signal processing in June last year. And what we did is we developed and obtained variants of the noise as functions of transmit signal and its bandwidth, and also the design parameters. And then the last one was long enough, and I just skipped these to do time about particle sampling noise and particle counting noise. And the last one was the chemical ligand binding noises. It's not reproducing papers, by the way, so I don't need it in my age, but the first two noises were long enough, and then also this third one was long enough and also separate, so that's why we published in two different papers. As in September 11, we studied this transaction signal processing, studied chemical reactions of the receiver, the ligand receptor kinetics noise. And then what we did, again, we obtained the variance of the noise as a function of the chemical parameters in terms of rates of binding and release reaction and the number of receptors at the receiver side. So now here's the picture that, you know, we are explaining the ligand binding process. That you know, ligand binding, as I told you, like the molecules are coming, these parts will be kind of binding, you know, sucking it, and sometimes it doesn't succeed, and then we lose them. And that's the kinetic noise we call it. Okay. And so now the next question was about, you know, capacity analysis. Can we rethink the entropy, for example? What is entropy here? And then accordingly redefine power consumption in molecular communication. So we did this work. How much time do I have? 10 minutes, 5 minutes? I'm over the time?
5 minutes.
Okay, yeah, 5 minutes. Oh, shoot. What time did we start? 11:10?
We can take 5.
Yeah, so we had a little bit, okay. So I don't want to hold you here. So we did information capacity analysis, but interesting here is, that's why there is a guy, A. Ben Naim from Israel. He wrote a book about goodbye to information, you know, the entropy with the thermodynamics. Here is we are mixing information theory and statistical mechanics, okay? In the information theory, we have quantification of information communication channel. In statistical mechanics, we have thermodynamic behavior of the systems composed of a large number of particles. You know, here, and then entropy energy, and then we have this physical reference model that we are looking at, which we did, and then we developed all these new capacity formulas. We published in Infocom last year, and so you see we combine information theory with thermodynamics, and then we calculated closed form expression for capacity as a function of bandwidth of the system, volume, temperature, and number of molecules and transmitted power. And of course, we use ideal gas because we want to find the theoretical maximum material information there. Okay, so then what else is needed? Research challenges. We did all these things generically, you know, like all these models that I developed, I presented to you. What will happen if we go to these specific cases, like molecular motors, calcium ions, bacteria, pheromones? Can we use our models? I don't think so, because they are generic and we need to do more detailed massage, but we can learn from those generic models. So we need to also analyze these separately, specific ones. And of course, all these issues that you said, heterogeneous like molecules, and then all these modulation techniques, you know, new ones in the chemical domain, and then interference. We also did analysis of interference, by the way. We have the paper, but it's not publicly available now. Multiple users interacting on interferences, and then a bunch of these protocols that may be developed. And my fear is, like many computer science people will take all these existing protocols and write tons of new papers. I hope they will not do it. Because, you know, taking AODV or DSR, whatever those, and writing them here, that will be fatal. Don't do that. So now the future will be, what we are doing is understanding these two domains from the communication perspective, like nanomaterials and biological, and then long term, after 10 years, hopefully, the people will continue, and then we'll look at the hybrid cases too. And so we got, after a lot of, it says nice story, but we don't have time to tell you this. We got $3 million. That's the first time in my 30 years career I asked $3 million, I got $3 million from NSF. So they didn't have budget cuts. But 26th of June, they grilled me and my team, we are 5 professors, for 2 hours. Tops of NSF. They had a bunch of questions, 2 hours. One guy was advisor to the President Obama in nanoscale, and there was like the biology director, NSF director, assistant directors, like they were, Bill Trenter was there, like 10 of them. They were asking questions. And after 2 hours, they say, we'll come back to you. And I couldn't sleep 3 days because I was in Barcelona. Will they give us or not? And finally, they said, we'll give you the money. But I was thinking, budget cut, nothing. So $3 million with 5 professors with mechanical engineering and biology. And then we have this money. It's also $3 million, hopefully, from the Department of Defense. Granite that I told you, the policies of Ken Paul from UT Dallas. And then we have these projects in N3 cut and quantum Molena and nano simulation. This will be a good addition to the NS3, by the way, simulation for molecular communication. Then we started this workshop, IEEE workshop. Last year it was in Infocom. This year is in ICC in Ottawa. And they have good papers now. So then we have a Nano Networking Summit in Barcelona every summer in June. That is with some Day that we go to parties after the summit. Yeah, the entire city's parties.
Given by Messi, right?
I wish. He should, yeah. I hope you know who Messi, some of them. Okay. And then I started the new Elsevier Journal 2 years ago. The idea came like many years ago, 3-4 years ago, but then we launched it in 2010. It's going really well. So I hope some of you will be inspired and start to do research. In fact, I have another activity now. You will say, wow, Samsung gave us money to study the drug delivery problems from the communication perspective. Samsung and that, right? So I had slides back at the time. So thank you again. I gave you this huge area that I could talk more and more. But if you're interested, go to our websites. And then the papers are there, information. And then I hope some of you will be interested to start to work on this. And don't be afraid of new areas. And I will close this section telling you a joke. In fact, it's a nice joke for all of us. It's also, we have those people. Like John, he's my host, and I can tell this because he's exactly on my side on that issue. I had friends, colleagues, 35 years ago, they were doing the same thing they're doing now. So the joke is, I mean, you did satellite and internet, that's why I can tell this, otherwise I wouldn't do it. So the joke is, a Greek old man comes to live with his father in New York. So he doesn't speak one word English. And you know, Mediterraneans want to be always independent, right? He hates to be always with his son. So he says, can you please teach me, say, coffee, bread, so that I can go and have my breakfast myself. So he teaches coffee, bread, and then, you know, so he's going every day. waiter, coffee, bread, and the waiter is also understanding, He brings always what he needs. After 1 month, he gets bored. He says, every day, coffee, bread, coffee, bread. And then he says to the son, can you teach me tea and croissant? So, tea, croissant, so he memorized everything. So he goes to the cafe, and today there is this one that he doesn't understand the foreigners, He says, what do you want to have, sir? And then he says, proudly, tea and croissant, and typical. What type of tea do you want to have? Black tea, vanilla tea, green tea, this, and then he says, what type of croissant? With chocolate, vanilla? He says, oh, coffee bread, coffee bread. So now, the story explains that very well, because I had colleagues, each time they come to a new domain, and it's not easy, guys. It took me many, many months, but it's exciting to understand, to learn, but then the payoff is more. But if you are afraid, you come here, you have some problems, like, coffee bread, you go, tea or croissant, you go back to your coffee bread. So you go back to your queuing theory and you do your queuing theory stuff. That's not good. That's not good. Why? Of course I respect them. But the problem is, seriously, because there are thousands of papers there. Maybe you have fantastic, solutions, but you don't get that much attention. And so it's better for young people, don't be scared to get into the new areas, but there are also these other extremes, right? They do everything. They do robotics, they do AI, they do mobile communication, they do real-time system. That's bullshit. I mean, they don't do that, because you're a wishy-washy man, everything. But, when you're a communication person, you move to new eras and new topics, and that's fine, like satellites, and like sensors, and whatever, and you do similar things, it's fine. But don't do that way, like I have colleagues, they're a man of everything, optical networks, as I said, operating system, database, this and that, that's not good. So anyhow, these are some advice from me. Thank you.
Thank you for very inspiring talk. We have a little bit of time for one.
Sorry about the time, guys.
Any burning questions?
They are tired of their money escape. Yes?
In your final example, when you're talking about the molecular communication, I think that you're using picking transport for the description of the molecular transport. But when you talk about molecular transport at the nanoscale, picking confusion starts to break down, becomes molecular confusion.
Yes.
How are you reconciling?
That's what we did that work. Remember, I used the word fixed diffusion,
right.
Brownian motion behavior,
right.
And then we analyze it.
Well, those are actually two different things. I mean, picking diffusion is the macroscopic description
Yes.
of Brownian motion.
Yes, that's what our assumption is.
Okay.
But that needs to be more and more investigated.
Yeah.
Like all this nanoscale level behavior and the different types of molecules, and also their according diffusions. We are doing all this slowly. We are analyzing now under these assumptions, and as we learn more and more, we go deeper to those cases of described.
I mean, you're right, and there's an additional question to what extent I can even talk about rates versus single bit communication models. So any other questions?
It's very interesting but complicated. If you want to jump immediately all those, it's very, very challenging. I mean, we want to understand from the communication perspective with these simplifying cases, and then learn as we go, and then fix our slides, and then, like in the first paper, we don't have any noises. But if you had that solution for a normal channel propagation model, people say, are you stupid? Forget it. Because there's no noise factor, but because it's new, with all these transmitter behavior, receiver, and then diffusion, people accepted it. So that's why, because it's something new, there are novelties there. Maybe it's not exactly what's happening, it's a model. That's why we learn. And then we went to the noise and then the interferences. So slowly we go deeper and deeper.
So you have 3.5 hours to think more about all these provocative thoughts and come back at 3 to 4. for a roundtable. If you'd like to continue the discussion. Okay. So let's thank Ian again.
Thank you. Next time when I come back, there will be 5 people.